studying forms of things, groups in particular, or varieties, is what we discussed last time. And since we anyway had a week break from that, and since anyway I should turn into some abstract nonsense at some point, why not doing it now? So this is in a big parenthesis. What we do now is non-abelian cohomology. This is a very general theory. Not very well known, but very, very, very useful in this setting of forms of varieties, etc. Descent theory, and I will discuss it now. So well, let's start with A being a group. G will be a group soon as well, but A in practice to be the automorphism group sample. So just let's get used to this notation. And A set X is a set, and node is an A action. Okay, we think it's simple. And now let's make an observation. Before this definition, X is principal homogeneous. A set if A acts simply transitive, not even stabilized for points, transitive on X. Also called sometimes possible. And by itself, without adding some extra structure to this story, this is a very dull thing. Example, maybe. Given A, can you give me an example? A with left regular, or maybe right sometimes. Regular. Somehow it will be. Of course, it is equivalent, but since I will change direction in the sequel, let's keep it right. A right regular action of A on itself. Now let's make some observations. One, this is the only one, up to isomorphism. Every principal homogeneous, every A principal homogeneous space is isomorphic as such to that action, to A action itself. Because, well, just pick a point and map it to one. And is this not clear to someone?
It's not canonical, right? So
No, this is not canonical. So maybe, how non-canonical is it? So maybe to answer this question, how non-canonical is this isomorphism here? We may ask, how many automorphism do we have to A itself? The automorphism of A as an A space, this is A is right regular action. That should be enough. So what is it?
A.
A. How does it act? obviously it's the only way.
What do you mean? What do you mean by
On acting on that A with the left. I will explain, but my purpose here is not to teach you something that you don't know. It's to remind you things and put it in the right setting. Left regular action. To warm up more.
nonsense?
Yes.
By the parentheses, you mean the set A with the right regular action?
Yes.
I mean,
So this is the
Then
set.
it's the set.
It's more than a set. It's the It's
with
the
the
A.
specific action.
Yes, this specific action. Right. And of course, A acts on itself also left regularly, and it commutes with the right regular action, and this is exactly the common counterpart. So those are very standard things. Maybe now.
So that's why you chose right regular action above, so you could choose the left below.
Yes, and some other reason. Okay, one else we choose sides, and we can play symmetrical. Okay, so as far as concerned, and this is what non-abelian homology is concerned of, I'm concerned about principal homogeneous spaces. There is no theory. There is one space with an obvious automorphism, but now I plug in another player. Now G, a finite group. I'm fixing now G to be a separate finite group. In this game, G will be fixed. A is fixed. I will vary the access. G finite group. Sometimes I will have to do with 4 finite groups, which is kind of a limit of the finite theory, and can make sense to discuss topological groups. Most of the time, I will just think of G now to be a finite group. In practice, it will be the Galois group of certain field extensions. A G group, or maybe A, is a G group if G acts on A by automorphisms. So any homomorphism from G to the automorphism, group automorphism of A, gives a G structure on A. And when I say A is a G group, I mean A is given with a fixed G structure, right? And I will fix now a G structure on A, okay? To most of this discussion. Actually, sometimes I will twist it in some precise sense, but now this is fixed to our discussion, and X, the set, is a GA set if X is an A set and also G acts on X in a compatible way. So this is not closed. Sorry. In a way. So with obvious notations, G of AX should be GA of GX. Let me give you an example. Maybe some sort of the easiest example, which is I will not complete later. G will be 1 and sigma. So it will be Z mod 2. Think of sigma as complex conjugation. Think of G as a Galois group of C over A acts on A by conjugation, by complex conjugation. A goes to A bar. Oh, this is sigma. Obviously, this is a group automorphism. In fact, G preserves the field structure of C, preserves multiplication of C, particularly on G, on A itself, which is a subgroup of C star. Right? So this is a group automorphism, nothing to check here. Now I'm asking you to come up, and really I will ask you to do it. I will not do it myself. To come up with X, a space. You can come up with many. I would be happy with any example that you can find. In particular, can you find a principal homogeneous A space, which is G space as well, which has a compatible G action?
Something like a conjugation of A and
Oh,
I.
A
What?
is a billion.
No, but something like I goes to minus I.
Yeah, okay, this is sigma. Okay. So Max's answer is the trivial one. That the same thing I'll say will work. The right regular action of A on itself is or gives, let me call it x1, which is A. Because I will ask you to now to think of x2, something else. The and AG, which is function, or GA. Whatever is compatible with this one. First, GA. Somehow G came first, fundamentally in this theory. Right? So the same action, take A with the same action, now think of X as an element in A, and the very fact that G is sigma here. G acts by automorphism on A means that A itself is a GA space. Fine. Let me draw a picture. Maybe it helps. Here's the unit circle. Here's A. Conjugation. Here's a picture of A. Takes points to, preserves, of course, these 2 points and reflect this air here. But another example, maybe this is, of course, a principal homogeneous space. Another example, of A, principal homogeneous of GA, principal homogeneous space, is to find.
So you mean principal homogeneous as an A set?
Yes, the principal homogeneity is as an A set. G is just, so it's like an extra structure of, again, there is some descent theory here. So you fixed that example. This is the only example of a principal homogeneous A space. And you kind of try to add a compatible G structure to it. Compatible on A itself, on the acting group, I do already specify a G action. I want to twist somehow, or deform, if you want to use this word, the action on the space A in a compatible way. This is the question I'm asking. I mean, or this is an equivalent question to the question of finding all principal homogeneous spaces. You may always think of your space as an A space, as a standard one, and the action as a twisted one. Okay? But now I want something concrete. Shall I?
So if you just rotate everything by
So then, if I rotate everything by 45 degrees, pi over 4 because we are mathematicians. If you took x2 is the brown dots here. So as you see, as a subset of C, the usual action by multiplication, A acts on it, and this is an A set. A preserves that. And of course, conjugation act on it. Now, it is completely different action. It's not, of course, it's not the same space, but it is not an isomorphic space. Because the G action here preserves 2 points. And there is no point preserved here. So we see that as a G, the G structure is genuinely different. And of course, it is compatible again with the A action, because everything is by conjugation, multiplication, etc. So is x2, as defined here, by nature. X2 is not isomorphic, this is what I just said, to x1. Of course, it is isomorphic as an A space, but not as a GA space. So remember, we are motivated, now I'm sustaining this, the geometric theory behind this, but we are motivated by isomorphism of spaces over a larger field extension. So if you ignore some Galois group action, but you want to distinguish such, you want to distinguish smaller field structure, which is the same as Galois action. I mean, and I need to make this precise, but now forget this. This is all behind. The formalism of what I'm saying is clear now to make the distinction between them. Of course, you can see that there is no isomorphism, and I already explained why, but being sophisticated mathematician, it's nice to come up with an invariant that we attach to spaces that distinguish these two, x1 and x2. Defined. I don't know, H0, the GX, ignore the A structure, just to be the G fixed point, we see that, and of course this set will be up to isomorphism an invariant of isomorphism class. So H0 GX1 is so fancy notation, right? But it's a good point to introduce it. Okay, so well,
But
yes.
of course, it's good the fact that you have to prove that this is the invariant.
Oh, this is an exercise.
Yes.
It is fixed towards the discussion. Just a remark. If and has a special point. Then, so, of course, it is a group, of course, there is a special point, but I'm emphasizing the fact that this is more than just a space here. This is I want to think of this as a pointed space. That is pointed space. Pointed space is a space with a point which is specified. This is kind of a trivial extra structure on a set. Okay. Why would one want to say? Because now I want to make definition. And now there are many ways to define it, but this is, I think, the easiest one to understand. Now I'm defining A1 GA, and this will be principal homogeneous spaces for G and A modulo isomorphism of GA spaces. So it's the classes of isomorphism of GA spaces. Here I claim that this is a space, a set, containing, for this example, these 2 points. Exercise. In the above example, A1GA isomorphic is given by these two guys, x1 and x2. Of course, there are isomorphism classes, to be precise. So you should prove, and it will be clear in a minute, that there aren't any more. Actually, if you're believing in a good choice of notations here, and since A is a billion, so this symbol makes sense as a classical group homology, so you know that you can compute it in whatever classical way you want, and you know that this space should be one-dimensional over the multi. So it should have two elements. Oh, and maybe a remark in accordance with the remark above. This is more than just a set. I mean, first of all, it is not a billion. As our grouping, but in general are not a billion, what you get here is a set, not a group, as in classical cohomology theories. But it's just a bit more than a set. It will be a pointed set. Remark H1GA is a pointed set. So we have a spatial element, pointed set. The standard, or that example here, the right regular action A itself with same G action is special. Always exists, and I call it a special element. Special in this sense. Okay, fine. Now, just before I go on, I think there is it is useful sometimes, and certainly classical, to give more than just this definition, but also a standard definition by means of cocycle equations, etc.
So what do you mean by pointed space in this setting?
So a pointed set for us is just a set with a point which I'm specifying.
Okay.
And I'm saying that, so I define this to be, in a minute, this will be very clear. This is a set, and not just. I mean, a priori, this is not a set, but let's not touch on that. So this is a set,
Mhm.
and there is always for every G and A that you
Mhm.
can specify there would be a canonical guy in it,
And
which
we
is
don't know.
the action of A in itself with the same G action.
So that's the remark in the.
That's that remark. That remark was about H0.
Yeah.
Okay.
Okay, now I understand. Yeah.
Okay, sorry. No dispute. Tiny, but okay. Now, as we observe, I guess I just erased that. As an A space, they are all principal homogeneous spaces the same. So, as we discussed before, just to specify a principal homogeneous GA space, I need to really find the action, the G action on A. Every principal homogeneous space is isomorphic and now we identify it with A with the right regular action. Okay? The G action must commute. Think of it as a left action. So I'm having some left action, so this is an action. So G A goes, let me denote it G dot A. G dot. GA is the given group automorphism action on A. So this is a bit confusing, but certainly not complicated. I am given an action on A by automorphism. I think now on this A as an A space, with respect to the right regular action, and I want to come up with a new action on it. Okay? So I will discuss this action, I will denote it by some extra, by this G dot. So it's different from that. Okay, so we should, I guess I can introduce another name to this map and use this, I don't know, rho or whatever, theta. I don't want it. I will just use this little dot here. Okay, is that fine? So denote A sub G. In particular, I'm having those special elements. I can encode the orbit of 1. This is the identity of A. I can look at each orbit. So this is a copy, full copy, but it's a map from G to A. I'll give a certain name, AG. Okay? And so if I denote this, then the action is given necessarily by the following formula. So G dot of whatever A should be G dot of A times 1, of course. Oh no, 1 times A. I mean, no, yes, but 1 times A, which must be compatible. G dot 1 times G of A. This is the action on the group A. This is the action on the space. So this is AG times I know the orbit of 1, and since the action of A on itself is transitive, if I know the G orbit of 1, and since the action is transitive and commute, the A action on A is transitive and commute with the G action, I know the action as a whole. Of course, I know the action everywhere. And it must be given by this formula. Left-hand side equals right-hand side here. Yes?
I'm a little confused. The action of G on A shouldn't be by group as an orthodox?
We have two actions. Yes, the action of G on the group A, which is given as an action by group automorphism.
So G dot might be...
G dot need not be an action by group automorphisms, right? This is an action on the A space A, or on a space which is isomorphic to A, as an A space. But when I write the dot here, then I'm acting on a space which I don't think of as a group, right?
So here the A is not a group. This is just
Well,
like that. Or this is the way you
A is a group.
A is a
Sometimes
group.
I
But this is
prefer
a
to
different
forget it.
action. This
I
is
thought sometimes I prefer to forget that A is a group
Mhm.
and just remember that it is a space, and though with an action of the group A. So I'm
Together with this formula is a bit confusing because the G action here is
oh yes.
Is on the other
So I
side,
should
right?
add dots here. Yes.
yeah.
Oh, no.
not exactly. No, that's
Here. Yes. And I guess when I
Because
wrote
the action
this,
here
when
is
I
from
wrote,
the right.
and maybe I should erase this notation. And when I wrote this, I was considering a left action. I had left actions in mind, and now when I consider the action of A on itself, then I discuss right action. I hope this is not that. Maybe I should, whenever I would say an A space, I should have said this is a right. I take. Here is the general formula of computability for GA spaces. And
Maybe the confusion is because you don't write what the principal homogeneous spaces are. So you start with a GA, principal homogeneous space, and you choose an isomorphism as an A, principal homogeneous space with the set A.
no, yeah, I can. Yes, I choose to. Yeah, okay. Yes. I said it differently, but it's the same. But yes, take any X which is principal homogeneous space, identify it with A, with the right action, and transfer the G action. So I can view a G action, the G action here, and then this will be done as isomorphism, of course, as an A spaces, and there is a unique G action here that will make this isomorphism a GA isomorphism. But so I forget all about other spaces and discuss G structures on A. Okay? And the claim that I made so far is that the G structure on A is completely given by the orbit of 1. Because then I can given an action and knowing those elements, I can tell what the action was by this formula. Now, but if you make an arbitrary choice, so AG, I may think of AG as a map from G to A, assigning to small g, small a. Small g, it assigns the elements AG. Sorry. So this is a map. These are elements of A, depending on G, so I can consider this as a map. Question that might arise is it always the case that whenever I have a map from G to A, it will give me an action? If it does give me an action, the action must be given by that formula, as I said. But then, how do you check that something is an action? Given a map G to A, G goes to, denoted by G goes to GA. The question is, does it give an action of G on A on the set, or the A set. A by the formula given here. G dot A is AG, G of A. This is a question now. So, in order to view this, I need to ask myself whether GH dot A equals G dot H dot A. So let's develop this. So this must be, of course, by the formula, AGH times GHA. Again, this here is the action on A by automorphisms. And this is, well, this is G dot of something. Let's do the something first. What is the something? Something is AH times HA. And now do G dot. Do G dot, think of this as an element of A, and this as an element of the space A, and this as an element of the group A. Maybe I'll write down in one more step. This is G dot of AH times G without dot of H of A. Fine? This equals, now let me open up this, explain what this dot is according to the formula that we have here. So this is AG times G of whatever inside times G AH, and this is G of H of A. So this is GH of A. By the fact that whatever is without a dot is an action. This I know. And this question mark here is the same as this question mark over here. So G to A, G goes to AG is an action, gives an action via this formula if and only if these things are the same. But I can cancel GH of A. If and only if AGH equals AG times G of H.
G of H.
G of AH. Thanks. And here, there is no dot in this formula. This is something that involves only the given action of G on A by group automorphisms. And this is called the one cocycle, or in our case, the cocycle equation. There will be no higher cocycle equations for non-linear homology, of this, in our discussion. It's called the cocycle equation. And I want to emphasize something. In whatever I will discuss, you don't need this. I only said it because this is very classical. I want to think about this case as something natural as the classifying space of all principal homogeneous GA spaces. Okay? Usually, if you understand the structure of things correctly, you don't need to write number equations. It's just, of course, sometimes we do, but this is a fact, and I don't want to ignore it, but this means that we don't understand everything properly.
Is there an option of a higher non-abelian cohomology?
So there is some H2, not really. And whatever is there, I'm not familiar with, so
Why you will use it to define the isomorphism of these guys? I mean, you expect that the pseudo-cycle or maybe a compoundry will be an indication of when these two things are isomorphic.
So let me discuss co-boundaries now. So questions. So I used this co-cycle equation whenever you have a map G2A of this form satisfying the co-cycle equation, I can go backwards and use it and use that formula over here in order to define a GA structure on A, a principal homogeneous space structure on A itself. And of course, up to isomorphism, by this way, I will get all of them. This follows from our discussion, right? So, the question that I must ask myself now is, doing this, when is it that I'm getting isomorphic, GA isomorphic structure on that A? So, when is given, I don't know, G to A, G goes to A 1G, and G to A, G goes to A 2G, 2 cycles, 1 per cycle, 3 per cycle, 2 per cycles. When are they, or when do they give isomorphic GA structure on the set A, on the A set A? Fair question, right? I used the cocycles to come up with a G structure on the A set A, the A right regular set A, and maybe what I'm doing is not. I can do the same thing up to isomorphism twice. Right. Okay, so so having two GA. I'm assuming now, given these two cocycles and the corresponding first and second actions, maybe when regard those, I will replace the dot by index 1 or 2 here. And so I'm having 2 actions on A, and I'm asking myself, when do they GA isomorphic? So if I have an isomorphism, the given, and I hope that my notation will be clear, A comma, or maybe rho 1 A and rho 2 A structures on A if they will be isomorphic, then in particular this iso gives an A isomorphism of the A set A. Oh, we are not lost in topologies. So, assuming I have A with two different G actions on the left, denoting rho 1, rho 2, corresponding to the co-cycles A1, A2. And the same, of course, given A action on the right. This is the two spaces I'm considering. And I'm assuming now they are absolutely isomorphic. So I'm having a map from A to A that commutes with the A action and intertwines the two G actions. Right? Then I'm given an A map, A to A, that commutes with the right A action and intertwines rho 1 and rho 2. Rho 1. So this map must be given by multiplication on the left, right? Which is an automorphism. Forget this part. It's an automorphism of the A structure, of the A set A. This map must be given by A goes to BA, no, by left. For some BA. There is some BA that does it. This is regardless rho 1 and rho 2. Now, specify this B, ask yourself, does it really intertwine rho 1 and rho 2? When is when do I intertwine rho 1 and rho 2? So this means that if I do B to any guy A, and then if I do first G1, I use a symbol O, I don't know why. G1 of A, and then I multiply by B, it should be the same as doing G2 after multiplying by B. Okay? This is my question. At some point I started to use the symbol O for generic action, I don't know why. For the G action. Okay, makes sense? This is the question of, does this map intertwine? It intertwines. Intertwine. Stop it. So, what is it? So this is given by B of G1A is given by the formula, somewhere written, this one. A1G times G of A, and this is given by the formula, well, I can do G2 of B times G of A. So maybe let's go one more step. G2 of B is given by that formula. G2 of B is given by A2G, G of B, and here's this GA. So this question mark here is that question mark here. So the answer, if and only if I have here an equation. If and only if A1G, so cancel this GA here. So if and only if A1G, that guy, is exactly the same as B inverse A2G. So any B that you can find would be an A isomer of the two actions. If it satisfies that, if and only if it satisfies that, then the actions are actually G isomorphic as well. So, two cocycle A1, A2 give isomorphic actions if and only if they are homologous. That is, to exist B in A such that A1G for every G. For every G in G. A1G equals B inverse A2G. Of B. And this is, of course, the classical cohomology relation between cocycles. A cocycle is trivial. It's trivial. It is a special point. If it is homologous to 1. This means that A1 will be trivial if I can plug A2 here. AG is B inverse G. It actually follows, but from our discussion, but let me give it as an exercise. Check that this cohomology relation, being cohomologous relation, is an equivalence relation, and all those things, all those co-boundaries are actually cocycles. They're all equivalent, of course, and so one may define classically. One defines what is the same, A1G, to be cocycles modulo cohomology.
So, this is what
But just wait, this is not a subgroup. This is an equivalence relation on that space. So note that.
you can view it as an action of A on the cocycles, right? If by
So there are various ways to view things as
and then
actions.
those are the only.
But no, there is no, there will be no action of A, or at least.
No, I mean on the
A
cocycle.
priori, no, this is not, or this. I see what you mean. So I may view this as an action. Anyway, yeah. So, indeed, you're right. So you may view this as an action maybe of A or the element B. The A given as a set of elements B, or the group of elements B, and this is the open space for that.
It's 1:30.
1:30. Okay, so it's a good time to stop. But so there is I will continue this after lunch. But I want to say again, I want to emphasize, one can make this definition and make this as some sort of an identification. For us, this is the definition. It's just a coordinate way of writing things down, and I will try as little as I can to actually use classical concepts.